Hello and welcome to FlexPDE topic number 6, normal elasticity. The first of 4 different topics on elasticity we're going to do, the other 3 being shear, bending moments, and torsion. Okay, so this first one, let's start off with this problem. We've got this extended beam and ABCDE with this little bit G there that's has this force applied on it, but we can replace it with an equivalent moment and horizontal force applied on this thing. And we've got another force here applied via point E. Then we have some reactions from the pins, and we have some spring forces acting on it, which are going to be related to the displacements. Now, the first thing that we can notice is that this creates too many forces on this for us to be able to solve without some more information. So for the equilibrium of this beam here, we're going to have that we get 2 force equations. So maybe net force in X we could use to solve for AX. Net force in Y we could use to solve for AY. And then the net torque about, let's say, point A, we would get, that's our last equation. But the problem is we have 2 unknowns. We have BF and CH. So we can see that CH times 40 centimeters has to be equal to BF times 15 centimeters, but that's the best we can do. We can only relate those two. We need one more equation to be able to figure out what the value of each of those forces is. There's infinite solutions right now with what we know. This is what we previously called statically indeterminate. It's not underdeterminate because it's supported. It is going to hold still. We just don't know exactly what BF and CH are going to be. But we can find it if we use some geometry and relate the fact that this, the amount that this spring extends is related to the amount that this spring compresses, and the amount that each spring extends or compresses are related to the spring forces, right? So let's see. We could, what exactly is that geometry? So if you say that the springs are so strong that this is going to move a very small distance in the vertical direction, let's exaggerate that. Let's draw it as if it moves a lot just so we can see what the angles are here. Then you can see that how much point E moves down, which we'll call negative YE. This is like the final coordinate of point E. Let's say the final coordinate would be YE. So this is like negative YE. So YE is like the amount that it moves up if this is initially the Y equals 0 line there, right? The y-axis where y is equal to 0. So negative YE being the amount that it moves down. Negative YC is the amount that point C moves down, and negative YB is the amount that point B moves down after the whole thing is finished bending. Right, so this being this amount that this point moves down, if this is a rigid object, is related to the amount that this point moves down because it's a similar triangle there, right? So you can see that YE divided by the sum of all those different distances has to be equal to YC divided by the sum of these 2 distances. Oh, wait, hold on. There's not a 15 there. That would be the point D. So just 15 plus 25, that distance, and that's related to YB divided by this distance, right? So this over that has to be equal to this amount over that whole thing, right? And that's equal to this amount over that whole thing. Okay, so with that, we can relate the displacements, just stepping back for a moment, we can relate the displacements of this point and this point together to the displacement of this point at the end. Or, you know, really there's those 3 different displacements are not independent. If we know what the angle of bend is, the tiny little amount that this is going to bend, then we can figure out the vertical displacements of each of these points. There's like one variable, 1 degree of freedom there, how much they bend. And that means the compression or extension of these springs are related. If you know how much this one compresses by, you know how much this one extends by. It's not the same because it's further out and this point here is fixed. So this is going to compress, let's see, this is 40 centimeters out. So if this compresses by 40 microns, then this one is going to extend by 15 microns because it's 15 centimeters out, you see? Okay, so those 2 are related in that way. So if you like, you can write out both of them in terms of this YE, and then write out what the spring forces are. So spring force BF the amount that it's pulling back on this beam with is going to be based on how much BF has extended. So if if point B moves down by negative YB, then the amount that it's extended is negative YB. So the spring force would be K times the extension. It's going to respond upwards with K times the increase in length that it has, and that's K times negative YBF because the other end is fixed. So the amount that this spring extends is based on how much this point moves down. The spring's on top, right? If this point moves down by 1 centimeter, this spring has extended by 1 centimeter. Then that we can relate to YE through the geometry that we just drew out. Okay, now same thing for CH. CH, this force, the force that this spring is pulling down with, is going to be based on how much this point moves up with, because that's the extension of that spring. Okay, so that ends up being plus YCH, which is, from the geometry that we wrote out, not with the plus 15 here, just the 15 plus 25, this distance over the whole distance times YE, the amount that point E moves up. So now, if we return back to this system, when we have our kind of 3 equations from the 2 force equations and 1 torque equation and 4 unknowns, it wasn't solvable. We couldn't find a unique solution. But now that we've figured out that actually these 2 reaction forces, BF and CH, have to be related, right? If you know the spring constants and you know how much one of them is, then you know how much it's moved by, and therefore you can figure out how much the other one must have moved by too, because they're tied to this rigid beam in the geometry, right? So through all of this geometry stuff that we did, there is a relationship between these 2 spring forces, and they're related through this displacement of the tip here, YE. Or you could have used any other point along the thing to write out the forces, but it's convenient here because the question was also asking us to figure out what the displacement of point E is, so we'll just write both of those forces in terms of point E's displacement. Okay, so then the 3 equations we'll have for equilibrium, plus the 2 equations that we have for the spring forces in terms of this tip displacement will give us 5 equations, and the 5 unknowns would be these 4 forces and that tip displacement. So now we're in a position that we can solve. So let's get solving this. The net force in the x direction says AX minus AX, so the net force to the right, I guess, minus AX plus 1E3 is equal to 0. Then in the y direction, we'll have AY plus BF minus CH minus 2E3. And then the net torque about point A, for example, we've got 15 centimeters, but which we could just keep in centimeters if it weren't for this applied moment there. So this applied moment is already in Newton meters, and if we don't put everything else in the newtons of these forces times the distance in meters, then we're not going to have we're not going to be able to add them to this Newton meter thing, or we'll have to convert this to Newton centimeters for it to have the right unit. So let's keep it in meters. 0.15 meters times BF. That creates a positive moment, one out of the page about point A. Then we're going to have minus 0.4, which is 0.15 plus 0.25 times CH. And we're going to ignore the height difference here for this 1K. We've assumed that we already took account of that displacement when we added this 200 Newton meter thing. But that is producing one that is rotating clockwise, meaning into the page. So that's going to be minus 200. And then similarly, this one will also make it rotate clockwise, minus 2E3 times this whole distance, which is what? 0.4, 0.55, 0.67? 0.67 times 2E3. Is that right? Let's double check that. This and this is like 2 20s. Okay. And then we've got another 20 that's a 60, and then the 7. Okay, looks good. All right, so that's 3 equations, and it's not enough, right? If you just try to solve this, we're going to get something from Maple saying we can't find all of them. We can only find some of them, like AX is uniquely determined. But the other ones you can only find in terms of one of the other parameters. So not knowing what CH is, we can't solve this thing totally. And how we resolve it is by putting in those 2 new equations that introduce only one new variable, the displacement of point E. So those were that BF is equal to KBF, and we'll have to tell Maple what that is, KBF times 15 over 15, well, this one's 67, we just figured out, right? Times negative YE. And the other one is CH is equal to KCH times 40 over 67 times positive YE. Right. Now we just need to put in those spring constants. I think those were up here. Let's put a new line, just so we can see them while we're typing. So we've got KBF is equal to 1E3 per millimeter, right? So to put it in newtons per meter, so that we are going to get newtons for BF, after we multiply it by YE in meters, we need to divide this by 1E negative 3, right? So that's newtons. That's converting it to newtons per meter. All right, and then KCH would be equal to 2E3 over 1E minus 3. So this is going to be like multiplying it by 1,000. So if it's 1 kilonewton per millimeter, that would mean it's a meganewton per meter. So these springs are likely not going to move all that much before they're producing forces that are quite large here. Okay, let's see. So with this extra information, we've determined what CH is, what AY is, what BF is, and also what YE is. So YE has ended up being negative, meaning that it's moved down. We put positive YE as the amount that it moved up. And that makes sense because these forces are generally downward. And YE is negative 0.003. So that means it's moved down by 3 millimeters in response to these, with these springs sort of holding it up there. And the CH is negative, meaning that CH is actually pushing up there. So this spring is in compression. It's been compressed a bit. And this spring is in tension. It's been pulled apart a bit. So it's going to be pulling back with 674. Now this spring is not nearly pulling back with as much force as this one. And there are two reasons for this. One, this spring has a lower spring constant. It's got half the spring constant. So for a given extension, it's only going to respond with half of the force of the other one. Two, because of the geometry, this spring has more than double the compression that this spring has extension. So because this spring is so close to this part, it's not going to be moving that much. If we got rid of this spring, then this spring would have to, then this spring would not be able to oppose it nearly as well because we're so much closer, right? So the thing would move a lot more. How can we do that? We can effectively get rid of the spring by setting KCH to 0. Let's see what happens. Okay, so the thing is still statically determinate, right? All of the equations still worked, right? It's just that now this spring can't produce any force. There's nothing in the problem that required KCH to be non-zero before. We have this thing moving a lot more. Instead of 3 millimeters, it moved 46 millimeters. And that's kind of impressive how much of a difference it made. So let's see why this works. We've got it to at half the distance, which means it's going to produce half the torque. And then it has half the spring constant, which is another factor of 2. And then there's half as many springs helping out. So it needs to do a lot more work. So those 3 factors of 2 give us like an 8. And from the rounding that it's really like 15 instead of 40 for the distance, that gets us to this extra increase in the displacement there. So it seems about right from a quick calculation, being, was that like 15 times as big for this, these like factors of 2 and a bit compounded up. Okay, so I've changed this back to 2E3 per millimeter. The spring constant back, we've gotten back the displacement that we had before, and I've made the free body diagram to use for the internal shear force and bending moment diagram. Okay, so now what we can do is assign this and then go off and write the equations for the internal normal shear force, and then bending moment. Okay, so the normal force is just equal to AX. That's it. There's nothing else that goes on. It's just AX at the start, and then we reduce it by, oh, wait, hold on a sec. We're reducing it by this 1E3 plus piecewise if X is greater than, what's that, 0.55, then negative 1E3. We're going to be subtracting 1E3 off of this thing. Okay, what about the shear force? V is equal to AY if we, plus piecewise if we go past the point of B, X is greater than 0.15, then we need to add BF. And the next thing happens at CH's force application. This is at X is greater than 0.4. Then we're going to be subtracting CH because that's going to reduce how much shear force we need to apply. And then finally, if we go past the end, we're going to be subtracting 2K. And that's X is greater than 0.67 we figured out earlier, negative 2E3. Okay. And now the bending moment, we can use the usual trick of the moment is equal to the integral of the shear force with respect to X. Well, X, let's make it a definite integral. X is 0 to X. And then just keeping in mind that we need to add in the applied moment as we cross point D. So if X is greater than 0.55, then we're going to be adding in 200. Okay, so let's see how this works. Plot N, V, and M from X is 0 to a little bit more than 0.67. Let's go 0.671, just to see that return back to 0 at the end. Okay, so that looks pretty good. We've got a normal force, which is 0 and then jumps up to that, jumps back down to 0 at the end. The shear force starts at AY, right? Dealing with AY there. And then it becomes more positive when we cross BF here. BF is actually directed up, yep. And then when we cross CH, it becomes a lot more positive because even though we subtracted CH was negative. This spring is doing a lot of the pushing up of this thing. And then we cross the last point here, and that deals with the final, once we cross the end point, that returns us back to equilibrium because there's no more forces on this, right? We would have solved exactly the same problem if the beam didn't stop there, but instead continued and had no more forces applied on it. So it needs to return back to 0 because we don't have any more internal force or moment. Okay, and same thing for the moment, right? The moment starts off here. There's no point moment applied at either end, so it has to go back to 0 at each end. And it's very smooth, right? It just has discontinuous slope wherever the shear force has a jump, and it has a discontinuity itself only when there's a point moment applied. So it's not really too bad to be able to deal with springs. We can deal with springs using the information that we had previously about how springs relate their force to displacements and a little bit of tricks of geometry. And then we can solve the kind of problems that we were solving last week with all of these forces applied and drawing internal force and bending moment diagrams, understanding what's going on with the beam, with the added benefit of kind of springs applied to them. Now here's the trick though. This week we're not actually going to be using springs per se on as applying force to these beams. Instead, what we're going to look at is the fact that any beam is kind of springy, right? You may have noticed the spring constants in that one were really high. And that's because if you actually took a thing that's not a spring and put it there in an attempt to hold this still, the reality is it is actually still a spring. It's a little bit of a spring that's going to be extending a bit and compressing a bit here, just by virtue of the fact that there's no such thing as a truly rigid object. So what we're going to be looking at this week is how to solve a problem like this, which is going to be solved in a couple of steps. One, we're going to be solving the problem of using information from physics and kind of like material stuff that you did a bit in first year to determine what the effective spring constant is for a beam like this, right? For this sort of thing. What's the spring constant of this? And then once we've got that, we're going to say, we're going to set up a problem just like this, which is really similar to the kinds of problems we were setting up last week with statics, but with the added complication of dealing with geometry to relate the displacement of one point to the displacement of the other point. This is going to be valid as long as you have one rigid beam here in green, one thing that can't bend or deform, mixed with other things that can and act kind of like springs because they have a non-infinite modulus of elasticity. So maybe this thing is steel with a really high modulus of elasticity of a few hundred, and then we've got, well, that's a pretty strong steel that would have that. But yeah, you've got a couple hundred anyway for steel, and then these beams are not as strong. They're like a weak aluminum that has maybe tens of gigapascals or even just 1 gigapascal. If it's some maybe polymer material, then they're a lot more springy compared to this harder material. So that's the sort of thing that we're going to be dealing with this week. 2 stages to the problem. Model the objects that can deform using physics to figure out their effective spring constant, and then use the different kind of physics like we were doing last week plus some geometry to solve for the equilibrium of an extended object impacted by these springs. So this week is only the first of 4 weeks on static elasticity. Well, I almost said it myself. Static elasticity, not electricity, but static elasticity, normal forces and stresses and response to them. And after this, we're going to be able to analytically solve problems with normal forces, that is perpendicular forces, and numerically solve problems with normal stresses and understand how stress and strain are related in 3 dimensions within a 3-dimensional bulk object. Next week, we're going to be adding in shear forces. So this week, we can still solve for the shear forces on a rigid object like this green beam and make diagrams like this, but we can't look at how these shear forces will make this object deform. That is going to take us a few weeks to build up in general. First, we're going to look at pure shear, which is if you have kind of symmetric shear applied to a total object, the same, it only is going to work if you have like this force here being the same as the force on the bottom going to the right, and it's uniform all the way throughout the thing. We'll talk about that next week. There's certain ways to set up a problem so that you're guaranteed to have that symmetric shear, and then we're going to be able to analytically solve problems with that and normal forces put together. This is called a pure shear or pure shear with normal forces together. And numerically, the thing we're going to build up in FlexPDE with that is going to let us solve any problem. In fact, this is going to be the end of changing FlexPDE, and we'll just apply different things to it and build up more analytical understanding over the next 2 weeks. How to deal with bending moments. So the response to this internal moment is going to take another week, and then after that, we'll be able to determine how this green beam should have deformed in response to these forces that we were applying to it. And then the very last of these ones is perhaps the most complicated because it's always 3-dimensional. We can't even, it doesn't even happen in this beam. We need to look at something more complicated to see this happening, a 3D problem that has the moment, so for a beam extended like this, a moment pointing in the right direction, which is the twisting in and out of the page, right? That's the twisting response. So we'll look at that in 4 weeks. So then, intro to elasticity. While for many systems it's a good approximation, there's really no such thing as a perfectly rigid body. Real materials do have some degree of elasticity. That is, they deform in response to the internal forces and moments that we calculated last week. Since solids are made up of atoms chemically bonded to each other and chemical bonding is governed by the electrostatic force, this means that, first of all, solids deform in response to force. They're not perfectly rigid, and that they're going to be exhibiting specifically a linear restoring force in response to the deformation, like a spring does, at least for small deformations. If you pull it too much, then that's not going to be the case. If the deformation is too large, then the restoring force becomes nonlinear, and this is the kind of thing you would have dealt with in first-year materials. We go from an elastic region into a plastic region, perhaps, and then fracture. And depending on the type of material, like metals might have a very large strain allowed in an elastic region, and then perhaps a quite large plastic region where you can permanently deform them but they don't break and then eventually fracture, whereas a ceramic will have all of its stuff in the elastic region over very little strain allowed but potentially massive stress allowed, and then no plastic region at all and just fracture if it's going to be having any permanent deformation, just going to completely shatter or break apart. So this is what we're going to be dealing with in this course is analysis of materials in the elastic region. All the stuff we're going to build up is going to require the linearity of differential equations that shows up in the elastic region, and that's what we're going to be able to solve. So this makes everything kind of like a spring, and everything is like a spring, at least if you don't move it too much. Okay, so we're concerned with these small deformations so that linear elasticity holds. We will be still looking at problems that you can't solve unless you do have numeric methods, even while sticking with linear elasticity. It's going to get quite complicated when we deal with 3D objects here. All right, axial stress and strain. Recall that a spring exerts a restoring force in response to a change in its length given by the spring constant, which is, we would say that the force of a spring is negative k delta x, where x is like the displacement of one end of it. Really, we meant that a spring responds by opposing a change in length. If you pull a spring into tension, it pulls back on you to try to compress. And if you push a spring into compression, it pushes back on you to try to extend. So we did this up here when we wrote this last spring example. We said that this has a force on this, BF, up, which is going to be positive if the spring is extended. So that kind of means that it's opposing the length change that happened in the spring. If we've pulled down this thing, if we have a delta y, which is negative, then we're going to be getting a positive force up, a force in the opposite direction. So that's the force of the spring. The force that the spring puts on other things is negative k times the deformation of the ends, right? If you've pulled this down, then the spring is going to pull up with a force of BF. But what is the force that has to be on the spring? Well, using a Newton's third law action-reaction pair here, you can see that the force on the spring is in the same direction as the length change. I mean, that's not so surprising. If you've ever pulled on a spring, it moves in the same direction that you pulled it, right? It responds with a force in the opposite direction to oppose that motion, but it itself has moved in the same direction that you pulled it. So the force on the spring must be equal to positive k times its length change. Right, so so if it has a positive length change, then you've applied a positive force where we're drawing the forces like this. So this is the convenience of putting the BF here as the Newton's third law action-reaction pair. When we drew this, we're drawing it in a direction. The reason it ended up being positive delta L is because this is really the force on the spring. We've already corrected the direction using the sign convention we built up 2 weeks ago to not have to reassign this when we go and look at the other thing. We've automatically used Newton's third law to figure this out. Okay, so any real material, again, will behave with some degree of springiness, so applied forces cause a length change proportional to that force, at least when we're in the linear elastic region. The spring constant for a beam with length L and uniform cross-sectional area A turns out to be this. It's inversely proportional to the length of the beam, directly proportional to the cross-sectional area, and proportional to a material parameter called the Young's modulus or elastic modulus or even just elasticity. And this has units of, well, we can figure it out. If this has to be newtons per meter, and we're going to multiply something by meters squared and divide by meters to get newtons per meter, then this thing has to have one more division of meters than this, so that when we multiply it by meters squared, we get newtons. Okay, so this is going to be newtons per meter squared, in other words, pascals, but typically more like megapascals or gigapascals for real materials. So this stiffness then is something you can think of as, okay, well, that certainly should have some like material parameter dependence. But what about A and L? Can we get some intuition around that? Why should it be proportional to the cross-sectional area? Think about springs like this. If you put another spring beside this, you double the area, then you've got two springs. And if both of the springs move the same distance, if you have them still extending by delta L, then they're going to respond back with twice the force. So of course it should be proportional to the area, just like for the same reason that two springs in parallel will have double the spring constant. And then what about if you put them in series? If you take a spring and then put another spring on the other side of it here, then when one of them moves, when one of them extends, they, for the forces to balance all the way along, they each have to have an extension that's only half as much as they would have had to if they were just the only spring there. So if you take springs and stack them in series, then that reduces the total spring constant, right? You can think about what's harder, pulling the end of this spring 1 centimeter or pulling the middle of this spring 1 centimeter if you're in both cases holding this still. Well, if the middle of this spring moves 1 centimeter, that's the same force as if the end of it moved 2 centimeters, right? So it's inversely proportional to the length. The longer the length, the lower the spring constant. Okay, so you take this spring constant, which again works for a beam with length L and uniform cross-sectional area A, and you substitute it back into the Hooke's law. F is K delta L, and then you have F is AE over L delta L, the spring constant, the thing that we just asserted here. So if you divide both sides by the area, you can get rid of the force and replace it with stress. And you can divide both, you can take this L here, you don't have to divide both sides by that, it's already here on the right, and use that to combine with the change in length, and then say, oh, well, really, this is the same as the microscopic scale expression for what's going on every little infinitesimal volume of this object. On any inside surface of this, the strain that it has is related to the stress that you're applying on that surface by the stiffness. So the Young's modulus is the ratio of an object's stress to the strain that it gets. The very fact that you can get this to work on a large scale, if it's a solid object, also requires this thing to work on a microscopic scale. On every little bit of it per unit, the force per unit surface area is the stiffness times the strain. So sigma, normal stress in pascals, and epsilon, length change per unit length, is the normal strain, which is dimensionless because it's a fractional length change. Let's go over some comments here. In this context, normal means perpendicular, again, just like the normal force. Unlike the force extension relationship, the stress strain relationship is only dependent on the material parameter. So this is independent of geometry, just depends on the material parameter. The normal stress and strain come in two flavors, just like we were talking up here about compression and tension. Tension, if you pull on it, it wants to pull back to compress, has a positive force. So tensile stress is the positive one. If sigma is positive, that means tensile by our regular sign convention. It means the object has been pulled apart a little bit, stretched out, and is trying to pull back. We're always writing the force on the object on a surface outside of it. So the sigma being positive is like a stress that's pulling apart the object. Yeah, and compressive one would be pushing in on the object, and that is that means the object, if we're applying that, the object has been compressed a bit by that stress we're applying and is trying to expand back out. So needs an inward stress. We need to keep putting that inward stress to stop it from expanding back out. So that's compressive stress. Tensile stress, you've pulled apart on it a little bit, and it wants to compress back. You've put it into tension. It wants to compress. It's in tension. Compressive stress means you've pushed in on it and it wants to expand back out. It is said to be in compression. 1 Pascal is a very small amount of stress in most contexts. So 1 Newton is about the weight of a chicken egg. So if you distribute that over the contact surface of about 1 square centimeter in your hand, imagine you're holding an egg and the part that's actually touching your skin of that egg with an open palm is about 1 square centimeter. If you've just got like a flat palm and you're holding this egg up, that is going to put a compressive stress of 1 Newton of weight of the egg over 1 square centimeter, which is 10 kilopascals. So 10,000 pascals feels like as much pressure as when you have a chicken egg held in your hand. That's not a lot of pressure. Maybe if a relative is yelling at you, like, are you going to drop that, you klutz, or something, then that could be a different kind of pressure. But the chicken egg itself, from a physics perspective, doesn't put much pressure on your hand. Now, so 1 Pascal is a really small amount of stress, right? It's a totally different story for one unit of strain, right? Strain is unitless. So a strain of 1 means that the object has doubled in length, right? This means the fractional length change, delta L, divided by the length change is 1. So it changed in length by as much length as it had originally. Strain of -0.5 means it shrinks to half its original length. A strain of -1 is ridiculous in the solid material context. That means it's kind of compressed to nothing and then expanded out in the other direction to its original length, like maybe folded inside out or something. It's not possible for uniform solid objects like steel beams, but it with some imagination, it could be applicable to some non-uniformly solid object like a sweater. So I hinted at it there, but the length you put in the denominator is the original length, right? If the length changes, don't use the final length, just use the original one. Now, in most practical purposes, the length that you have is really small, right? A strain of a large amount is not going to be happening in most situations, right? So if you have a strain that is 1e-4, it doesn't really matter whether you used the length before or the length after. You're going to calculate pretty much the same strain because the length change is so small compared to the original length. Okay, let's look at some typical values here. So here's some relatively stiff materials. We've got silicon, which actually, to be able to use it, we're going to need to deal with non-isotropic materials, which we're going to bring up in the topic of general elasticity. But to deal with isotropic materials like tungsten, everything like that, all these metals, they're going to behave the same in different directions, and they have Young's moduli given in here. Okay, so tungsten has a really high Young's modulus. It's a very stiff metal with 400 gigapascals, and we got a softer metal like lead with a Young's modulus only 16 gigapascals. Still, we're in like the gigapascal range here, billions of pascal per square meter is the kind of Young's modulus we're talking about here. So what does that mean? It means that if you push on a cubic meter of lead and you want to move it by 1 micron, you want to push in on that so that it's going to move by 1e-6 meters, you are going to need a kilonewton of force per every gigapascal that you have in its stiffness here. So this means it's going to take 16 kilonewtons of force to compress lead by a cubic meter of lead by 1 micrometer. It's going to take 400 kilonewtons of force to compress a cubic meter of tungsten by a 1 micrometer. So these are very small distances for a cubic meter to be compressed by, right? That's only 1 in a million. That's 1/1,000,000th of its length. So that's a strain of 1/1,000,000th. And these are pretty big forces, right? So the weight of 16,000 eggs or the weight of 400,000 eggs, that's quite a lot of force that we're applying on the side of it. And that's why the approximation that a lot of solid objects aren't that springy, that they don't move very much, is a pretty good approximation. But if we're concerned with dealing with statics and how much stress they are going to be responding with so that we can still solve problems like this one, then we need to calculate those things. Even if they're small displacements, by knowing how the displacements are related, we can still relate the force that this has to the force that this has by using the displacement as an intermediary. So metals have this yield strength where there's a certain amount of stress applied to them and they're going to no longer behave elastically. So you can see that the yield strength, let's say for copper, is almost as high as its Young's modulus, except that we're in megapascals here rather than gigapascals. So that means that a little bit less than 1/1000th strain, than a strain of 0.001 or 0.1%, copper will leave the elastic region. So you can strain it to 0.1% strain almost and have it still behave elastically. What happens past that? It doesn't break. You can strain it a fair bit more than that, and it still will not. It still will not break. You can, if you give it time, you can draw it into a wire, of course. But so if you think of copper as pretty flexible before it'll break, that's true. You can draw copper into a wire. But once you've drawn it into a wire, if you let go, it doesn't snap back into the bar that it was in before you drew it into that wire. And that's all plastic deformation there. So the snapping back would mean if you could draw it into a wire elastically. So a material like copper will not behave like that. A material like rubber can come a lot closer. So for these materials we're talking about, they break around 0.1%. Silicon is really remarkable, can go up to 80 times the strain of most metals. But rubbers could have strain limits over 100%, right? Like you can imagine taking an elastic band and quite easily stretching it to double or even triple or perhaps quadruple its length. And it's not about being shaped like a spring or something like that. Those sorts of materials can have much higher strain limits, but they're very, very special and used for the very large strain limit that they can have and the large elastic response of them. For a typical metal, an elastic response that is much lower than that is more typical. One other thing to note is that these materials can have, well, some materials anyway, can have different strain limits in tension and in compression. So the same piece of concrete might have 0.7% as a strain limit in compression, but only 0.01% in tension. Concrete is notorious for being way stronger in compression than in tension, and that's one of the reasons we use reinforced concrete in building. What you do is you take some concrete, before you pour it, you put these steel rods in the area that you're going to pour the concrete into, and then you pull the steel rods apart so they're tensed a little bit, maybe 0.3% for this piece of concrete. Then you pour the concrete in, and you wait for it to harden, and then you release the tension on the steel so that it is going to be compressing and putting some stress on this concrete. If it ends up having the right combination of area and amount that you stressed it by, maybe it puts the concrete to 0.3% compression by default, and then the concrete could expand out by another 0.4% before. Well, it could, if it's compressed by 0.3, it could expand out by 0.31% before it gets to this limit, and it could compress by another 0.4%. So that's a way to get more range on how much stress the concrete could take by pre-stressing it. If you have a material with a vastly different strength in compression than tension, just make it so it's always in a bit of compression, and then if it gets something to put it into a bit of tension, it is handled by the other material there, like the steel in that case, which turns out to be perfectly fine in tension. All right, let's do an example of this. So suppose we have a compound cylinder with loading. So you have a cylindrical rod here with a 90 kilonewton force to the right, and we're going to pretend this is uniformly distributed over the cross-section. Then we have two 65 kilonewton forces to the left on this junction part, and then a 45 millimeter diameter rod here, which has a 40 kilonewton force to the right on this end. Now we have all the length, the lengths of different sections along the bottom, and because of these forces, this segment is going to be in compression, pushed together, and this part here is going to be in tension. It turns out there's no force in here because these forces all end up canceling. Otherwise, we would need a reaction force at the left, and it would maybe be pulling or pushing depending on what these forces were, and then we'd have some stress in this section, and maybe this would expand or compress. But as it is, we have only this part compressing and this part extending. And our goal is to find the axial stress in the regions AB, BC, and CD, and then find the total deformation of the composite rod ABC and the deflection of this point C. Okay, so we're going to start off by writing out the normal force. So the normal force is changing as we move along. This is using the same sign convention as before. So first it's going to be the reaction force at the wall, which again is 0. So there's no normal force for this part. But once we go past an x of 0.3 meters, then the normal force is going to be reduced by this 90 kilonewtons, because that is going to mean the internal tensile force has to be negative 90. Will be in 90 kilonewtons of compressive force internally. So minus 90 E3. Then as we pass point C, x is greater than 0.5. Now we're going to be adding 130 kilonewtons from the 265s that we've got in the other direction. Then just to close it off and check that it works, we can do piecewise x is greater than 0.9, the total length of this, and add in negative 40 E3. Okay, so we can plot that, and from x is 0 to, let's go a little bit past, let's go to 1, and it looks like it works. We've got 90 kilonewtons of compression here, negative 90, only on the part between B and C. And then about, it looks like 40, like exactly 40 kilonewtons of tension over here, positive force over on this side. All right, so next thing, to find the stress, we just have to divide this force by the area. Now we can do this systematically with Maple if we put in what the area is in each different section. So first let's put in the diameter, maybe call it diam, is piecewise if x is less than 0.5, let's say less than equal to 0.5, then the diameter is going to be equal to 0.06 meters. And if x is greater than 0.5, then we've got 0.045 meters. Okay, so there's the diameter, and the area is equal to pi times the diameter squared over 4. All right, so here's what the area looks like. It looks kind of funky in there, so we can do a bit of a check. Let's substitute x is equal to, how about 0.4 into the area and see what we get. And maybe we'll evaluate this thing. So we get 0.02827. What if we just took 3.14 times the radius there, 0.03 squared? Do we get the same thing? Yes. What if we put in a different x? X is 0.7, the one that's in the second part, and we put in half of 45, 0.0225. Yep, looks good as well. Okay, the differences are because we used real pi in here instead of 3.14. If we use just that, then we should get exactly the same thing. Yeah. Okay then, the stress is going to be the internal normal force divided by this area. So we can get rid of those checks and put in sigma is equal to normal force divided by the area. And we don't need to report that. Well, I guess we can look at it. It's going to be a ratio of piecewise functions, so it looks kind of nasty when you look at the form there, but we can certainly plot it. And there we go. So the plot of that is very similar to the normal force one, but divided by the area one. We could plot that as well, I guess. Plot area. Sure. So, oh yeah, I guess the area one, because they're both positive numbers, is sort of scaling there. Maybe let's go, how do we scale that? We'll go y equals maybe area. Let's just call it a equals 0 to 0.03. Sure. Wait, what did I do there? Oh, I scaled the wrong one. I meant to scale this area one by that. Okay, great. So now it's showing you the area is on a, well, I went up too high there, but the area is similar for these two. It's like a factor of 2 different or so. And because of the factor of 2 difference in the force here and the factor of 2 or so different in the area, the stress is more or less similar, right? We've ended up with about 30, what is this? 30 megapascals, 30 E6 of compressive stress here, and about close to 30, like 28 or so megapascals of stress in the other direction. So tensile stress here, because this is being pulled apart, and compressive stress here, because this part's being pushed together. So that's good. I mean, that's the first part of the problem anyway. That's the axial stress in each of these regions. Now, what about so axial normal, meaning perpendicular to the cross section along the axis for this cylinder. What about the total deformation? So how can we find the deformation? We can relate the deformation in any little bit, the length change in any little bit, delta L, through the strain to the total length. The problem is that this is not uniform. We know there's no strain here, and then this whole section, we could find its length change, and since this part doesn't move, then we could say what the total length change to the right is of point C by looking at the length of this part over which the strain is uniform, right? So we could say that delta x of point C, maybe we'll make a variable for delta x. Let's call u the displacement. So u at C, u at x equals C, would be equal to 0 times L AB, the length from A to B, because there's no strain there, plus epsilon in BC times the length from B to C. Yeah? So this should be the total displacement, the displacement of point C in the horizontal direction will be the length change in this first part, because the left side doesn't move at all. That's critical for this to work. And the length change there is the strain there, which is 0 times its length. And then the length change of BC, which is the strain in this part times its length. Okay, so we could figure that out using Maple. Let's put that over there. And then we can go up to this part and just substitute that in. So we can say UC is equal to epsilon in BC. Oh, how do we find epsilon? First, let's find epsilon. Let's find the strain everywhere. And we can do that by putting in the Young's modulus, which they gave us in the question. The Young's modulus is 70 E9. And then epsilon will be equal to sigma divided by Young's modulus. So we found out up here that sigma is equal to Young's modulus times epsilon. So epsilon would be sigma divided by the Young's modulus. Okay, so sigma divided by Young's modulus is our epsilon. And now we can substitute x is equal to something in here like 0.4 into epsilon times the length of this section, which is 0.2. And that should be the total displacement of point C. It looks like a mess, but if we evaluate it, we find that we have an answer here. It's moved about 91 microns to the left. Now, I know what you're thinking. You're thinking, Dr. Minnick, isn't there a way that we could do this with integrals? And you're right, absolutely. So, I mean, why have this macroscopic thing here when you could revert this to saying, you know what, this total displacement, this u that we've gotten, the displacement when we have the left end fixed, is just the strain times the total length change that we're talking about. So in a differential sense, for a little tiny piece of it, the little bit of extra displacement that piece has gone must be equal to epsilon times the little bit of x displacement that we have. So if we break it up into a bunch of little pieces, dx, then we can see the little bit of extra displacement that comes from that is the strain there times dx, which then lets us go and find out what the total displacement is at some point by integrating epsilon dx from 0 to x. Okay, well let's try that then. How about we write out what u is as the integral of epsilon from x is 0 to x, and then we plot that from 0 to 1. So let's have a look here. We start off with no displacement until we get to point B because there was no strain in there. And then in this part where we have a compressive strain, we have a negative displacement. The part that's moved the most to the left by this 90 microns we calculated is point C. And then as we start to move to the right from there, this part's in tension. So this is moving back more towards the right. There's a spot in this bar that hasn't moved at all, right? Some spot maybe about here if we were maybe 0.7 or so down, so 0.5, about like right in the middle of there. That part hasn't moved at all because the amount that this is compressed, this part has tensed by, this is compressed by, so this is moved to the left, this part is held still, and then this part here is moved out by a bit. Right, so moving a little bit further, the point to get to 0.9, that's not 0.7, that's like actually 0.7 would be sort of in the middle there. That's closer to, what is that, 0.6, 0.8, 0.7 would be in the, I'm seeing 1, 2, 3, 4, 5 divisions. Yeah, so this is 0.76 actually. Right, so, okay, not quite in the middle, but a little bit over here perhaps, has no displacement, and then the point to the right is displaced a bit more to the right, because the tension in here over a longer distance has given us a bigger thing for the integral than this area did. Okay, so the right part has actually moved a little bit to the right in response to all of these forces. So this same principle, this idea of relating the stress internally and the strain and the force via the Hooke's law equation, is going to allow us to now set up problems like this, where we have a rigid bar and have a support over here and another support over here, and figure out how the forces are related in more complicated setups like this one. So in the figure shown below, the rigid bar ABC is pin supported in the middle there and is connected to steel rods, that rod and that rod, which have a Young's modulus that's given as 200 gigapascals for this particular steel. And the rods are AD and CE. The rods are 8 millimeters in diameter, so not very wide rods, and they're threaded at their upper end with a pitch of 2 millimeters. This means per rotation of this nut, it's going to move down by 2 millimeters. Okay, after being snugly fit, the nut at A is then tightened 2 full turns for good measure. Why not, right? Okay, so what's that going to do? It's already snug, and then we tighten this 2 more turns. So we lower this end of the rod by 4 millimeters, or equivalently, we try and put enough, we put enough tension in it so that there's some kind of balance, right? Really, if we tighten this 2 more turns, we're going to have some tension in this thing and some tension in this thing so that they're going to balance. The net result is going to be, compared to horizontal and balanced and everything, we're going to have 2 millimeters more of 2 millimeters total of extension in these rods. So maybe this one is extended by 1 millimeter and this one's extended by 1, or this one's extended by 2 and this one's 0. That's not going to work because then the force won't balance, right? You see how this works? So if this one is extended by 1 millimeter, then the tension that it's going to be putting back on this will be too much, because they have the same diameter. This is shorter, right? It's only 2 meters. This is 2.5 meters. So with 2 millimeters of extension in this rod, it's going to put more tension, and the tension has more of an effect on this because the pivot point is farther away for this one, so that's not going to create a torque that balances, right? So you sort of see how this thing plays out. What has to be true in this case, let's get some new space here, okay, is that we got a new Young's modulus, which is 200 E9. The net torque about point B is going to be equal to, actually, you know what? Let's do this properly. Let's start with a free body diagram. We've got our paint.net open. And sure. Actually, you know what? Let's go into a totally new one. Why not? So here we go. And we've got got an object there. Yes. And we're going to write that there's a tension force down on this. Let's go a little bit larger. And we'll call this, what was that, A and D? Yeah. So this is force AD on that one. And we'll put a bigger font size. Yep. And then we're going to have force CE over on this one. Okay. And there's going to be another force up in the center, which is going to be, by inspection, AD plus CE. So we don't need any horizontal force there. We just need AD plus CE up. But what we're really concerned with, that sort of is by applying the force in the y direction equation already. What we're really concerned with is finding out how strong AD and CE need to be. So the net force in y has kind of given us this balance. And now we can do the torque equation. So the torque equation says that 0.2 times AD has to equal 150.15 times CE. So that's not quite going to solve it, right? We have one equation and two unknowns. So what we're going to do for a bit is we're going to rewrite these in terms of the displacements, and that's still not going to get us anywhere. But then finally, we're going to introduce some geometry that relates these two displacements. It's the geometry of this that's going to say the amount that this one moves down by is related to the amount that this one moves up by. And that's going to finally bring it to a close. Okay, so first step is to say that AD, the tension force here, would be equal to the stress in it times its area. Sigma AD times the area, right, the cross-sectional area. And we can write that out. That's the same for both of them. Area is equal to, they said it was, what's the diameter? 8 millimeter diameter. So the area is equal to pi times 0.008 squared over 4. Then, so AD is equal to the stress times the area. And similarly, for the other one, CE is equal to the stress in CE times its area. Now, what about the stresses? Sigma AD is equal to epsilon, the strain in this thing, epsilon AD times the Young's modulus. And then same thing for the other one. So the stress in CE is equal to the strain in CE times the Young's modulus, same Young's modulus. Now what about the length change? Well, these strains, epsilon AD, are equal to the change in length. So the strain, the tensile strain in AD is equal to the upward y displacement, y AD, the amount that this point has moved up, divided by the original length, which is 2 meters. And same thing for the other one. So epsilon CE, strain in this one, is equal to the amount that it's moved up, YCE, also divided by the length of it, which in this case is 2.5 meters. But there is a bit of a trick here, which is that we have pre-tensed this nut. So we've turned this by 2 full turns, 4 millimeters. That's a start. So you can imagine the starting point, this holds still, and then imagine for like an instant, we did that turn really quick and we put 4 millimeters of tension into this rod. So if we let YAD be the final coordinate of this end of the, I guess I should call this YA, the y coordinate of A, and this thing the y coordinate of point C. Yeah, if you let YA be the final coordinate of point A after this is all settled, then there's some default tension in it, right? If this is 0, if this has not moved up at all, then there's already 4 millimeters of tension built into that rod by the twisting of this nut there. Okay, so then what's so far we haven't done anything, right? We haven't helped, really. We've put in a lot more physics, but we haven't gotten anywhere. We have this one relationship, and then we just turned the force into stress, and we turn the stress into strain, and we turn the strain into length change, building in some stuff and information all along the way. But what we need to bring this to a close and finally lead it to another equation that doesn't just introduce another unknown and not get us anywhere from a math perspective. What we need to do is add in a relationship between this y displacement and this y displacement. And the relationship is the fact that they're on this pivot point together. So imagine this one moves up, then this one has to move down, right? In fact, the amount that this moves up over 200 millimeters has to be the amount that this moves down over 150 millimeters, right? So we can say that YA over 0.2 has to equal the amount the other one moves down is negative YC over 0.15, right? So that means one of them has to be positive and the other one has to be negative, right? Like YC itself has to be negative, the amount that it moves up has to be negative for YA to be moving up in a positive sense. Okay, so let's run that and see what we get. So here's what we get. As expected, the force in AD is smaller than the force over in CE because AD is farther away and we need that for the pivot to happen. So AD is indeed a bit smaller than CE in force. What about in displacement? It is farther away, so it has to be more displacement than point C. And so YA is larger than YC, and YA is the one that is negative. Why is that? Well, we tighten this side, so just from an intuitive step back on the whole problem point of it, when we twist this thing is the one that has to move down, and this one moves up. Okay, that makes sense. We tightened this one. But this thing is still in tension because it has a positive strain, epsilon AD, and that strain is not actually as big as the strain on the other side. What's going on there? How can it move down and still have a positive strain, meaning that it's in tension? That's because of this nut. So we built in this extra 4 displacement anyway of this rod if this point doesn't move at all. So it has a 4 extension, then moved down by 2.7 millimeters. So that means that it's like 1.3 millimeters of net extension. Now point C has 2 millimeters of extension, so it has more extension, which given that it's longer, it needed to have anyway to have the same strain, but it has more than the proportional amount that you would expect to have even more strain from that even more displacement. So this is the epsilon, right? Epsilon CE is larger than epsilon AD, and this is what's required for it to have a higher stress and therefore a higher force. The geometry in these problems can get kind of challenging. So here we've got a rod which is held by 3 identical wires, and the wires are spaced apart evenly. So we have a distance of L between each wire, and then we have at this location X, this force P, which is applied to this rigid rod in the perfectly downward direction. So we're going to assume that the wires don't move that much, they don't deform that much, but we can find out what the force is in each of them by using the same techniques that we had before. The geometry is going to be a little bit more complicated to write out though. So let's take a new thing and draw that in, and then let's, you know what? Here's another thing you can do. Before pasting that, let's add a new layer, and then let's paste it, and then we can select different parts of it and eliminate them. So I might go and eliminate that, and now just draw in the vectors. Let's get the right color there. Sure, get rid of the other arrow. So we'll call this force A, and then we've got force B, and we've got force C there, and there's force P down in that spot, and we also have a displacement. So let's imagine that the thing has moved. It's deformed a little bit. So we've got that it has moved, let's say, to new locations. And we'll put the displacements as these things. So maybe we'll call this YA, measuring Y in the downward direction, sure. YB, and YC over here. Okay, so with this drawing, we can now go and write some relationships between all of these different things. So let's start off with the net force equations. So we have FA plus FB plus FC minus force P in the downward direction. Then we can write a torque equation. So that's going to be, let's say, about point A. We're going to have L times FB plus 2 times L times FC minus X times P. Next up, that's it for the statics equations. You can see we've got a lot of unknowns. Let's pretend that the length and X and what P is would be known. The basic problem why we couldn't have done this before is because we have 3 unknowns, these 3 different forces, but we have only 2 equations, the force in Y and the net torque about some point. The force in X is trivial because there's no forces in X on this thing, so it doesn't help us at all. So how do we solve it? Well, we next have the relationship between each of these forces is going to be dependent on how much the thing has extended by, so what these y's are. So we can say that FA is equal to whatever the spring constant of this wire ends up being times YA. And then even without knowing what that spring constant is, if all the wires are the same, then we can also say that FB is K times YB and FC is K times YC. Next, we can use geometry to relate these extensions together. We're going to get one geometry equation that tells us the whole thing. One way to think about this is imagine that YC is known. Okay, it gives us to gets us to this spot. And then YB is known as well. Then you will uniquely know where YA is because it has to still lie in that line between the other two. So while this could be anything and then this one could be anything, once you know those two, you know what this is. Okay, now that's easy to see from the geometry that in this particular case, because we've added one more L, what you've got to do is take whatever YB is and then add this distance. But that is exactly the same as this distance, right? And this distance is YB minus YC. So therefore, YA is equal to YB, kind of the starting distance here, plus that extra distance, which is YB minus YC. The slope times the extra displacement L. Yeah, so even though you could simplify that to 2YB minus YC, because of the way that we concluded that we came up with that, it's probably better to leave it in the direct formula there. Okay. Now this is not going to be able to solve because we have a whole bunch of unknowns, but really we want to know what some of them are in terms of the other ones. So let's pretend we're just looking for the forces and the displacements. This should be solvable for those 6 things. As a check, we have 6 equations. Okay, so we can solve it for 6 unknowns, the unknown forces and displacements. With everything else, like the spring constant, presumably the force P here, and X and L would be known. Okay, so let's check. Some of these things matter. Some of them actually don't. So just intuitively, what should not matter here? If we know what X is in terms of L, then it shouldn't depend on the answer shouldn't depend on that, right? Because these are going to go to the same displacements depending on what X is. Now the Y's might depend on L, but they might just kind of scale with all of this? They're going to depend on k anyway. Let's see. So it turns out that the y's depend on k, but they don't actually depend on L. If you know what x is in terms of L, that will cancel. And YB is proportional to P over 3 times K. So whatever the force P is, 3K, why is that? Well, we have 3 different springs kind of holding this up. Yeah? So that kind of makes sense. If this was placed right in the middle, then B would move down that much, and pushing it off to the side doesn't change how much the middle one moves down, but does change how much A moves down. So if X is smaller, we'd expect this one to move more, right? If we're putting the force closer to this side, and this one to move by the same amount less. Let's check. So compared to this one, P over 3K, YA is, if X is 0, then it will move by like 5/6 of P over K. How does that compare to P over 3K? Oh, if you multiply numerator and denominator by a half, then you can get this to be 2.5 over 3. So that'll be 2.5 P over 3K. So it'll be a lot more if we move P all the way over here. Then in this particular setup, this point will move down by 2.5 times the amount that this point moves. And similarly, YC should be kind of the same thing, but plus that, moved up by that amount. By symmetry, if we haven't made any mistakes here, then if we put X is equal to L, we should have exactly the same thing over here. So yeah, that'll get us to a, if X is equal to L, we'll have a 5 there. So like a minus, or sorry, not if it's L, if it's 2L. If X is 2L, then we'll have minus 6L plus L is minus 5L with the minus in front canceling. That gets us to the same thing we had earlier of 5P over 6K. Yeah, okay. So this is an example of how you can solve a more complicated one. In the particular version that they told us, X was equal to 2 over 3 times L, and that simplifies the results a fair bit. We have whatever the spring constant is scaling the Y results. YA moves the most, YB moves kind of a middling amount, and YC moves the least. This is a third plus a sixth, and this is a third minus a sixth. So it's balanced about point B in the center, all in a line there. And we have similarly the forces being proportional to the displacements through the Hooke's law relations that we had. So because A moves the most, it also ends up carrying the most load compared to B and C. All right, next up is Poisson's ratio, the axial coupling in stress and strain. So axial coupling, meaning that the x direction stress and strain is actually coupled to what's going on in the y and z direction. If you take a free object and you compress it in x, then it's going to expand in y and z typically. So really the x, y, and z stresses and strains are all related through a parameter. The parameter here, nu, Greek letter nu, not a v, a nu, is called the Poisson's ratio. So the x strain is not just the stress in the x direction, the axial stress in the x direction over the Young's modulus. It turns out that you could also get x strain, because you can also get x strain by compressing it in y. Let's say you have a negative y stress, right? You push it together in the y direction, then it could also expand in x. So that means we have a kind of the opposite relation for y to x compared to x, right? To get it to expand in x by using an x stress, you have to pull on it, tensile stress in x, to expand it in x, positive strain. But if you only have access to the y dimension and you want to expand it in x, you don't pull on it in y, that'll make it shrink in the x direction, right? If you want this to move up, what you could do is push on it in the y direction, yeah? And then same thing in z. If you push on it in z, it'll also expand in x. So the Poisson's ratio is the coupling from one axis to another. You see this? This is writable as a matrix. if you take your X strain relation in terms of the stresses in the 3 dimensions, and then Y and Z, and cast this into a matrix, it looks like this. So you see that the X component of stress causes what? It causes a strain in X through this first component. It causes a strain in Y through the second component, and it causes a strain in Z through this third component. Remember how matrix multiplication works? If you want to multiply a matrix by a vector, what you do is dot product each row of the matrix by that column vector. So M times R is going to be the first component here times X plus the second component times Y plus the third component times Z, all added up, and then same thing for the second row dotted with that, and the third row of the matrix dotted with that to get the last component. In Maple, you can do it with this. So you include the linear algebra package, and then you can type a matrix like this, matrix, bracket, and then put an open square bracket for the list of row vectors that you're going to add with those things as lists as well. Now you've got the matrix there. So this is saying first row 1, 2, 3, second row 0, 1, 0, and then third row 0, 0, 1. And let's suppose we want to dot that with X, Y, Z. The dot operation is just a dot, right? So we say M dot R, and it will dot this matrix. It'll left multiply this matrix by that vector and give us this result. Try it out. So now you can see how this relationship between stress and strain that we wrote up here works, right? This first column of the matrix is telling you all of the things that are going to be multiplied by the first entry in this vector, right? Because we're always going to be dotting this row by that column to get the new result. So this first row is telling you how the stresses in all 3 directions convert into strains in X, while the second row is telling you how the stresses in all 3 directions convert to strains in Y, and the third row is telling you how stresses in all 3 directions convert to strains in Z, right? But what the columns do is tell you how the X stress leads to strains in all 3 dimensions, how the Y stress leads to strains in all 3 dimensions, how the Z stress leads to strains in all 3 dimensions. Man, the visualizing this is tricky, but very helpful for understanding really what we're talking about here. So what does Poisson's ratio mean? It tells you how much coupling you have from one axis to another. A material with a lot of Poisson's ratio, of really high material, like a really high Poisson's ratio material like rubber, will tell you that stresses in other dimensions cause strains in different ones very effectively. So 0.5 is like the theoretical limit of Poisson's ratio. 0.4999 is a very high one, right? This means that if you have a stress in Y, it'll cause like a tensile. Let's suppose you pull on it in the Y direction. It pulls out by a certain amount in Y. Y strain will be proportional to that over E. But then you have opposite that strain in the other 2 directions, but multiplied by the Poisson ratio. So imagine you get it to expand by 10% in Y. Rubber, with its Poisson's ratio of nearly a half, will be compressing by not 10%. So if it expands by 10% in Y, it'll be compressing by 5% in both X and Z. A material with no Poisson's ratio, though, like, well, we don't have one here, but cork has a Poisson's ratio of very close to 0. That means it doesn't actually expand in Y and Z when you compress it in X. You can picture holding a cork or a sponge, right? And you push on it in one dimension and it doesn't expand in the other. So that's what a very low Poisson's ratio is like. Compare that to rubber, which when you push on it in one dimension, it expands in the others by exactly what you lost. Another example of a very high Poisson's ratio is a water balloon, right? A water balloon has a Poisson's ratio of pretty much 0.5. It perfectly preserves volume, but doesn't resist shape. It doesn't resist shape changes. So you push on it in one dimension, it'll compress in that dimension, yes, but it'll expand by the same amounts that it compressed by in the other dimensions in a way that preserves volume. To do that, it needs to have a Poisson's ratio of 0.5, not 1, right? A Poisson's ratio of 1 would mean that it actually expands by more in the other dimensions, right? Like you compress it by 10% and it expands by 10% in both of the other dimensions, means the volume has increased. So you can't have Poisson's ratios higher than 0.5 unless you do wacky things like this this folding chair. This is possible. This allows it to have negative Poisson's ratios in some cases. So imagine you pull on it in X. What it'll do is it'll actually expand in the other direction as well, not just in the direction that you pulled on it with. So this is an example of, with really wacky interactions between materials, how you can have Poisson's ratios that don't quite behave like you would expect. Poisson's ratios that are different from one direction to the other, and Poisson's ratios that are even negative. Let's look at an example. Suppose you have a cube and you're going to apply a tensile stress in the x direction to an otherwise free cube of side length L that has an isotropic Young's modulus E and Poisson's ratio nu. Calculate the new dimensions and the change in volume. So because it's otherwise free, that means that the stress that we're putting on it in y and z, we're not going to resist motions in y and z. Those are going to be 0. So if we jump back to our strain is 1 over E times this matrix times the stresses, and put in 0 for y and z, then we can calculate out by just multiplying through this matrix what the components are of their strains. So the strain in x is going to be this first row times that, which ends up being just sigma x, and then we bring the 1 over E inside and it becomes over E, and the second row times that, it'll be this first negative nu that still survives, and then same thing for the third row. So here's the new strains. Remember that strains are delta L over L, the change in length per unit length. So the new dimensions, the L primes, would be equal to the original length, L prime, is equal to original length plus the change in length, yeah? And original length is actually kind of included in this change in length. So this is L plus delta L is, let's remember, that strain is equal to delta L over L. Whoops. So that means we could rearrange this and find delta L, change in length, is the strain times the length. So then if we substitute that into here, then you can see that we have L times 1 plus the strain is the new length. Okay, so we're just going to do that in each of those 3 different dimensions, x, y, and z. And by substituting in these things that we found, we see that the new x dimension is the original length times 1 plus the stress over the Young's modulus, right? So this kind of helps understand what stress really does. If we apply a stress that's, and what Young's modulus means, if you apply a stress that's 1/1000th of the Young's modulus, you'll get it to go to 0.1% longer length, right? But in the other dimensions, it'll compress to that same 0.1%, or by, I should say, not to, but it'll compress by that same 0.1% times the Poisson's ratio. So if the Poisson's ratio is 0.5, it'll compress not by 0.1%, but by 0.05%. If the Poisson's ratio is 0.2, then it'll compress by 0.02%. Yeah. Okay. Visually, you can see what's going on here. We pull on this red cube, and it extends in the x direction. We're sort of exaggerating the dimensions here. It extends in the x direction and then compresses in y and z. This really should be kind of extended by more in x than it's compressing so that it conserves volume. It looks as if the compression in y and z is about the same as the extension. No, it should be at most a half of the extension for this to conserve volume. So maybe it's extending a lot more on this side than we have on this side, and we just can't see it. All right, what about the volume? How do we calculate what the new volume is? Well, the new volume would be the product of all of the different lengths, because this is still a rectangular prism. So we can just multiply all the lengths together, and that'll be this thing, right? So from these being the new lengths, we multiply those, and we get L cubed times the product of those things. Now, because the strain is typically very small, we're going to have 1 times 1 times 1 as one of the terms. Then we're going to have epsilon x times 1 times 1, and epsilon y times this one times that one. We're going to have epsilon z times this one times this one. Then we're going to have other terms that involve multiplying 2 epsilons together. And we can write that using big O notation like this. This is very common in talking about the efficiency of computer algorithms, among other things. But this means plus terms that are at least going like epsilon squared. And those terms are going to be really small. Because epsilon's very small, we don't care about order of epsilon squared terms. Epsilon being like 0.1% means epsilon squared is 1 in a million, right? So we can pretty much ignore that and say that the new volume is basically L cubed times 1 plus the sum of the 3 strains. So the change in volume, and this is why we even needed to keep the strains next to the 1, because that 1 is going to cancel when we figure out the change in volume. We'll have the original volume minus V, and that'll mean we're subtracting off just 1 times L cubed. So we have L cubed times this. Right. So the fractional change in volume would be just the sum of the 3 different strains. And this is going to work unless the strains get to be very large. Like for something like a water balloon, you might have strains that are 50%, and then this dropping of the order of epsilon squared term is no longer so valid. So all of this stuff where we say the new volume is L cubed times the sum of the strains, that actually didn't need us to be in this specific example where we're applying just a tensile or just a stress of sigma x in the x direction and leaving it free in the other directions. That would have still been true no matter what stresses we were actually applying here. But if we do substitute in this particular case where it's free in the other dimensions and just stressed in x, we can know what the sum of the strains will be. It'll be this thing plus these 2 things together. So we'll have sigma x over e in all 3 terms we can factor out, and we'll have 1 minus 2 nu. And this tells you a little bit about what the Poisson's ratio is, right? This kind of puts numbers to this thing we were talking about before. If nu is 0, then the volume change is directly just like this length change that we would have in that one direction, because it doesn't compress in the other directions at all. But if nu is 50%, if nu is 0.5, the volume change is 0, right? This goes to nothing. It means that when you extend it, when you pull on it in one direction, then it compresses in the other directions by just enough, by half as much, in a way that perfectly preserves volume. So what nu is kind of like the degree to which a material resists changes in its volume more than it resists changes in its shape. So for rubber with nu of almost 0.5, the object is much more resistant to changes in volume, right? You can easily deform it, but it takes up nearly the same space. For cork, though, it doesn't resist changes in volume at all more than shape, right? Cork will just extend in the one direction, and the other dimensions are just like, whatever, that's happening. But for a water balloon or rubber or something with a high Poisson's ratio, it'll compress in those dimensions to allow that extension to happen. You can think of it like the internal molecules don't want to be pulled apart, but they don't care about the shape and the organization of them. Whereas for cork, they don't care at the molecules can be pulled apart quite easily, and it's like the 3 dimensions are totally independent. Okay, let's put some specific numbers to it. Let's suppose the beam is originally 3 meters by 1 meter by 1 meters and is made of steel with these parameters, and we're going to apply a 200 meganewton tensile force to each end of the long section of the beam. So that is the x sides, the positive x and negative x side. Calculate the deformation of the beam if the beam is otherwise free. So we need to figure out what the stress is. And the stress is going to be this force divided by the area of that face. Now, conveniently, the area of the face is a 1 by 1 square. That's the y and z dimensions. That would be the area of the plus or minus x face. So the stress would be 200 megapascals, because we'll just divide this 200 meganewtons by 1 square meter. So it ends up being 200 megapascals. And when you substitute that into there and put in the 200 gigapascals for the Young's modulus, we end up with a strain of 1e minus 3, 0.1%. And then the new length would be the original length plus the change in length, where the change in length is the original length times the strain. Right? Remember that the strain is delta L over L, and we have uniform force all the way through because there's nothing changing things as we move along. It's just like a beam where you have a force on one side and a force on the other side. So the internal normal force will be the same all the way along the thing, and the area doesn't change. So we have the same stress everywhere inside of this 200 megapascals as the stress that's all the way along. So that means that we have the situation of uniform stress. And with uniform stress, we can say that the strain everywhere is also the same. So that means that this strain, we can just multiply by the original length to get the change in length. And if it was 3 meters long, then we have a 3 millimeter length change. Now just think about this for a little bit. Let's try and make it real. So we've got, like, really picture this 1 meter by 1 meter by 3 meters steel slab. That's huge, right? This is a big piece of steel. And we're going to take a 200 meganewton force and put it on each end of the long section of this beam, right? That is a massive force, 200 meganewtons. How much is that? That's it's hard to put it in egg terms now because it's hard to visualize this. That's what 200 million eggs weigh, right? What about the weight of a car? A car might have a mass of, like, depending on the kind of car, maybe 2,000 pounds. 2,000 kilos, right? 2,000 pounds would be a pretty light car, but 2,000 kilos is on the heavier side of a car. And so let's take this larger car that has a mass of 2,000 kilos and figure out how many newtons that is. You multiply by basically 10 newtons per kilogram. So that means that a heavy car has a weight of 20 kilonewtons. Okay, so how many cars are we talking about here? So you take this steel beam and you put not one car hanging from it, but to get to 200 meganewtons, we're going to need 10 cars would give us 200 kilonewtons. So this is 10,000 cars. So we have 10,000 cars hanging from this object, this steel beam. And when you do that, the steel is going to extend by 3 millimeters. It's a 3 meter long beam. You hang 10,000 cars from it. And in the axial sense, you put them all so that it's just tensile. It's not going to bend the beam. You don't put it like a sideways force. We'll deal with that in a couple of weeks. But for now, just in the extension thing, 10,000 cars will extend this steel by 3 millimeters. Wow. Now, how much is the compression in the other directions? We get a strain in those directions, which is Poisson's ratio times the strain we had in the x direction rather. So the strain in the x direction was 1e minus 3, so negative nu times that gives us a negative 0.3 e minus 3. And with the length change being only 1 meter in those dimensions, that means we've got 0.3 millimeters of compression in the other direction. So this beam, when you hang your 10,000 cars on it, will be 3 millimeters longer in x and 0.3 millimeters narrower in y and z. If you can do that force if you can make that force apply in a uniform way. Okay. Now, follow-up question. What if you don't fix both ends of it? Right? Maybe you can picture this, but instead of hanging the 200 meganewtons from one side and then pulling back with 200 meganewtons on the other side, what if you only pull with 200 meganewtons on one side of this? What's the deformation now? Well, 0 mostly, because now it's not in static equilibrium. You need to apply that force on the other side to hold it still, right? If you just apply the force on one side of it, then it's going to accelerate off to infinity, just accelerating again and again, like forever and ever until it blows up. We'll see that when we don't apply the boundary conditions correctly in FlexPDE being one of the solutions that shows up. Okay, so let's talk about a different way to look at some of these things. You'll hear this defined in some areas that are involving statics. If you apply a uniform pressure to some side, like an internal compressive stress that's the same on all different sides of magnitude P on all the faces of it, then you're going to get it to compress. So the fractional volume change, which is negative, is equal to the pressure, but we'll say it's proportional to this pressure that you're applying, where the proportionality constant written down here in the denominator is a material parameter called the bulk modulus. This is like the elastic modulus, but for volume change instead. So the larger the bulk modulus, the more pressure you're going to have to apply to get the same fractional volume change. The reciprocal of bulk modulus is called the compressibility, which, because elasticity engineers have a twisted sense of humor, is given the symbol beta. So we're going to use beta for compressibility and K for bulk modulus instead of compressibility and bulk modulus, like you might have guessed. Yeah, this is not the end of having the backward symbols for different things. It's not even the end today of having backward symbols for things. We can relate the bulk modulus to the Young's modulus and the Poisson's ratio by solving the uniform pressure problem using axial stress and strain. So this thing that we just did, imagine we take our axial stress and strain relationship, stress and strain, and we put in negative P as the stress in all the different dimensions. So we're applying an inward pressure, which means it's a compressive stress of just P in the axial direction, right? Pressure is like the normal stress, but inwards on an object, rather than the default of dimension here being positive is tensile, yeah? So if we substitute this in, then carry out the multiplication, we're going to have the same thing in all three dimensions, which is 1 minus 2 nu times our negative P over E. And from the work that we did earlier, figuring out that the fractional volume change is the sum of the strains, we can now just add these three things up, and we'll get negative 3P over E times 1 minus 2 nu. If we compare this to this equation up here, you can see that the bulk modulus, K, is equal to E divided by 3 times 1 minus 2 nu. So the bulk modulus is directly proportional to Young's modulus. You take a material, you double the Young's modulus, other things equal, you double the bulk modulus. And it also is related to the Poisson's ratio. So the higher the Poisson's ratio, the more bulk modulus you're going to have for a given Poisson, for a given Young's modulus. Elasticity is like the resistance to stretching in one direction if it's totally free in the other directions and you don't care what they do. Whereas bulk modulus is the resistance to volume change from applying a uniform pressure on all different sides. So let's put some numbers to this and calculate the bulk modulus of a few different things, rubber, copper, and cork, in terms of their respective Young's modulus. So what's the bulk modulus relative to the Young's modulus, which is to say what's K over E. So for rubber, it is 1670. For copper, it's pretty much 1, and for cork, it's 1/3. And what this means is that the fractional volume change you will get if you put in a pressure of 1/100th of the Young's modulus of the material is very different for the three different things. So for rubber, with a pressure of 1/100th of the elastic modulus of rubber, you'll have almost no volume change. It's like 6 parts per million of volume change. For copper, you'll have a fractional volume change of 1% if you put in 1% of the Young's modulus of pressure. Whereas for cork, you'll have 3%. You'll have more than you would have thought from just the Young's modulus, because you're applying this pressure in all three dimensions, and the dimensions are pretty much independent in cork, right? So you compress it by 1% in X and Y and Z with this pressure on the three different sides. Yeah, think of like a sponge, how easy it is to compress the volume of that compared to how easy it is to compress the volume of a water balloon. Like it's that water that stops you from compressing the volume. It'll move around like the rubber, but will not allow you to change its volume very easily. as a follow-up exercise, rank rubber, copper, and cork in terms of compressibility, in order of compressibility. So which one has the most compressibility, which one has the least? You might be tempted to think, aha, rubber is the least compressible because its fractional volume change from putting on a pressure of 1/100th its Young's modulus is almost nothing. But remember as well that the Young's modulus of rubber is quite small. In fact, it's the smallest of the three. Young's modulus of rubber is 1,000,000, while the Young's modulus of 1,000,000 pascals, that is 1 megapascal, whereas the Young's modulus of copper is 120 gigapascals. So it's way higher, 120,000 times higher than rubber's Young's modulus. So even though this fractional volume change is very low compared to copper, like 6 parts per million instead of 1 part per 100, the vast difference in the elasticity of rubber compared to copper means that rubber is actually a fair bit more compressible than copper is. So rubber's compressibility is about 6 times 10 to the negative 10 per pascal. Copper's is 8.5 times 10 to the negative 12 per pascal. And cork's is 1.6 times 10 to the negative 7 per pascal. So copper is the least compressible. Rubber's about 70 times as compressible as copper. And even though its relative This is because even though its relative bulk modulus is 1,700 times higher than copper's Young's modulus is 120,000 times higher than rubber's. Cork's Young's modulus is higher than rubber's as well, but only by a factor of 20. So cork is still by far the most compressible, 270 times as compressible as rubber is. All right, stiffness and compliance matrices. This improved Hooke's law relation that we've been using, rather than the one-dimensional one that now incorporates the Poisson's ratios and the changes from other dimensions as well and allows us to deal with these different stresses, is so useful that we're going to give names to this matrix in front. We're going to say that this thing is the strain vector, and that this thing over here is the stress vector. In general, we're going to be in the 11th topic just talking about these as not vectors, but arbitrary kind of n-dimensional things called tensors, which are like vectors, but n-dimensional. Yeah. So a vector is like a rank 1 tensor. A scalar is a rank 0 tensor. A matrix is a rank 2 tensor. That's the common thing for all of the things that transform like these do, tensor. Okay, so the matrix that relates this vector, stress vector, to this other vector, the strain vector, is called the compliance matrix. Why is it called the compliance matrix? Because the more compliant the material is, the more it's going to move, the more it's going to strain in response to a given stress. Okay, so the matrix here, the whole thing, not just the thing in here, but including the 1 over E that we factored out, is the compliance matrix because it relates this stress to the strain like this. You multiply the compliance matrix by the stress vector and you get the strain vector. Okay, so again, compliance matrix, given the symbol S, tells you the strain from the stress by left multiplying by the stress. An isotropic material, which is everything we're going to deal with until topic 11, is one that is going to respond the same in all different dimensions, and it has a compliance matrix that looks like this. You just need the Young's modulus and the Poisson's ratio, and you know all of the terms. All right, the inverse of the compliance matrix is the stiffness matrix. Right now that we know this is the matrix that relates stress to strain, it turns out this is invertible, and you can find out the stress, if you know the strain, by left multiplying the strain vector by the stiffness matrix, C. Yes, for some reason, S is the symbol we use for compliance, and C, therefore, is the symbol used for stiffness. If you think this is silly, you are correct. Also, we park in a driveway and drive on a parkway. I don't know what the source of these is, like why we use the opposite terms. Maybe the words mean maybe like S is the start of the word for compliance in German or something. If anybody has a good explanation or is able to dig up on the internet what the history of using backward symbols in elasticity is for things like bulk modulus and compressibility, for things like stiffness and compliance matrix, then I would like to know. Please let me know if you do find out what the history is, why everybody uses the opposite letters from what the words start with here. Maybe it was designed by the same person who decided that certain natural gas cylinders need to be threaded backwards just to make sure you're definitely, I don't know, like thinking and not accidentally opening it when you're trying to close it. Well, that seems like a weird thing to do. Thread it backwards just so that it opens the opposite direction. So if you think, oh, I better turn this gas off, well, let's thread it backwards just to make sure people are on their toes whenever they're operating this. That seems like a weird decision. Right. So as if statics wasn't tough enough, we have the opposite symbols for these matrices. So maybe it's the same decision. You've got to be thinking whenever you're using them. The way to return to it is to remember that they're the opposite. So S is the one used for compliance and C is the one used for stiffness. And to remember what each matrix does, that one you can think through. So the compliance one, you multiply the stress by the compliance. If it's more compliant, it'll have more strain in response to that stress. If it's more stiff, higher C matrix, then it will have more stress in response to a given strain. For it to have that strain, a material that's very stiff will need a lot of stress applied to make that happen. All right, so here was our compliance matrix. What about the stiffness matrix? It's supposed to be the inverse, so we can figure this out in Maple by including the linear algebra package and then defining S as 1 over E times the matrix of 1, negative nu, negative nu, negative nu, 1, negative nu, and negative nu, and 1. That should work. Okay, and now let's take the inverse of this. C is equal to matrix inverse of S. Like that. Great. Okay, so there's our C. And let's see if we can write this in a different form. Simplify mod. Not really. We can take some terms out of it. Like we could decide to factor some stuff out of that. It is possible to simplify out in front this thing, E over 1 minus nu times 1 minus 2 nu. You could carry this out yourself and try and do it algebraically, but if you don't want to do that, you could at least try out dividing this thing out and checking that it works. So let's try to factor that out. So we're going to divide out an E, and let's look at this. If we divide out E, then you see the same thing without the E inside. If we pulled out the E, that's like dividing E if we're going to multiply it in front. So then by the same logic, we can multiply by 1 plus nu and 1 minus 2 times nu and see what it would look like after we factor both of those things out too. Aha, and there we go. We've got the 1 minus nu, the nu, 1 minus nu, and nu, 1 minus nu. Yeah, so there we go as a demonstration that this factoring that we did actually works. So let's explore this a little bit. Since nu is less than 1, we want to write it like this, and this gets across the fact rather than like negative nu plus 1, it writes out exactly where the things are positive and where it's negative. So we could write Hooke's law via stiffness using now the stiffness matrix as the stresses are equal to this thing times the strains. And let's explore this a little bit. The off-axis terms of the compliance matrix, which was this one from earlier up here, are all negative, right? But the off-axis terms of the stiffness matrix are all positive. Why? That seems a little bit weird. Can we think through what this means and why it might be the case by applying some loading conditions? Yes, we can. So let's try that out. If we apply a tensile X stress to a material that's otherwise free, then it's really easy to see how that works out by using the compliance matrix. Because if it's otherwise free, we can put in 0 and 0 for the stress components in the non-X direction. And then we can multiply this across and see what we get. So this says if it's otherwise free, applying this X stress will make a negative strain in Y and Z. And that is exactly the example we did a little while ago where we pulled on this cube in one dimension. It was free in the other dimension, so it compressed in those dimensions. All right, that's fine. What about the strain example? What if we fix it to have no strain in the other dimensions and force a strain to happen in X. Now, to fix no strain in the other dimensions, that means you're holding it still in those dimensions. You don't allow it to compress when we know that it would want to. If you just kind of pull it out in one dimension, that's this example, that's applying a stress in just X and allowing it to compress in the other dimensions, that's what it would do naturally by this. But if you don't allow that, you force the strains to be 0 in that dimension, then what this equation says is you need to have applied a positive stress in those dimensions to do that. And that kind of makes sense, right? For a free object, meaning you're not applying any stresses in Y and Z no matter what happens, you just apply a tensile stress in X, you pull it apart in X, and it will compress in, it'll have a negative strain in Y and Z. So if you want to stop that, fix it to have 0 strain in Y and Z, you need to have applied a stress which would counteract that. And it ends up being, not surprisingly, positive. So you need to apply a positive stress to stop it from compressing. And this is why we end up having all positive components in the stiffness matrix, but the off-axis components are negative in the compliance matrix. Off-axis components in the compliance matrix tell you that stressing it in one dimension, other things equal, will lead to compressive strain in those dimensions. Off-axis components in the stiffness matrix tell you that straining it in one dimension, other things equal for strain, will lead to a requirement on tensile stress in those other dimensions as well. Something else showed up as a result of this example that you might not have expected. So all we've changed is what we're doing to it in Y and Z. In this example, we say totally free in Y and Z, do what you want, beam. In this example, we say, no, hold still in Y and Z, you're not allowed to move. And if you look closely, the relationship between the X stress and strain is not the same in each case. This one is telling us that the X strain will be the stress divided by Young's modulus. So that is what we've been using as Young's modulus. That's kind of the basic stiffness. We said sigma is equal to E times epsilon. And that turns out to be true only if the material is free in the other directions. If it's fixed in the other directions, we can rearrange this one and see what the new relationship is, right? If you're holding it still to have no strain in the other directions, then what you have is E times 1 minus nu over 1 plus nu times 1 minus 2 nu times epsilon is equal to sigma, not just E. And the size of this thing is going to be higher because nu is positive, right? I've gone and filled this out in a table for you. This thing here is known as the effective E, right? It's the effective E in whatever situation. The effective stiffness in the X direction is if you just take the stress and then divide by the strain in the X direction, then that's how stiff it feels, right? If you don't know what's going on in the other dimensions and you just kind of like pull on this thing, it's going to feel like it has the stiffness of the effective stiffness, the stress divided by the strain. So this is a definition of effective stiffness. I guarantee people in the chat are going to say, what effective stiffness? I've never heard of this. Well, here it is, effective stiffness. It is just the stress divided by the strain. So you do some experiment in the object, like you put some stress on it, you see how much strain you get, the ratio is the effective stiffness. Okay, so the effective stiffness, if we have it free in the other dimensions, is just actual E. But the effective stiffness, if it's fixed in the other two dimensions, is E times this thing. And this thing is higher than 1. If nu is 0.01, it's basically 1. It doesn't make much of a difference. So something like cork, you'll have basically just the same Young's modulus as your effective stiffness, even if you fix it in the other dimensions. But for rubber, if you stop it from being able to compress in Y and Z, or expand in Y and Z, you hold it still in those dimensions, then the effective Young's modulus is about 1,700 times higher in the X direction. Wow. So this can be quite an important thing to know for materials with high Poisson's ratios. What's going on in Y and Z will affect what's happening in X. This idea of effective stiffness is useful for figuring out the effective spring constant and points out how we can have complicated relationships for that depending on what's going on in y and z. So remember at the beginning, the introduction to what we're doing this week is to first figure out the effective spring constant of the beams that are supporting our like main beam, and then use geometry and statics to figure out to figure out how this thing is going to be moving. So we're going to have the same statics equations that we had before, and maybe be able to draw internal force and bending moment diagrams for this thing. But we are going to need to relate using geometry and effective spring constants how the forces on this beam are applied. Well, one of the things that affects the effective spring constant is something that affects the effective stiffness, and that is how you are treating the material in the other directions. If it's totally free in the other directions, the effective stiffness is just the Young's modulus, but if it's totally fixed in the other directions, it can't move in those, then the effective stiffness is this thing, which can be quite a lot higher if the Poisson's ratio is large. So that brings us to the next section, 2D simplifications to 3D problems, plane stress and plane strain. Plane stress means that the Z dimension applies no stress. So we're going to be using this as a way to solve a two-dimensional problem where we don't care about what's going on in Z, just like we've done in the last couple of weeks, over the last couple of weeks, because there's nothing interesting in Z. That's the case for some problems. And if the Z dimension applies no stress, like it's totally free to move in that dimension, then you might use the plane stress boundary condition and just substitute that in and only deal with the problem in 2D. So that is going to look like this. We're going to say the stress is 0, and when you substitute this in, you can find out that the strains will be related by only a two-dimensional matrix, which you can invert to find a two-dimensional compliance. This is the compliance matrix, two-dimensional stiffness matrix, which is going to work as long as the assumption that led to it is correct, which in this case plane stress means the stress in Z is 0. But you could also imagine that you're looking at one slice of a very large object in the Z dimension so that it can't move in Z. It's like fixed between walls at the end, or it's very large, and no motion in Z can take place. So in those circumstances, you might consider that you've got plane strain instead. This means the Z dimension has no strain. And like this, it's hard to see what matrix you would use, but if we jump instead to writing it in terms of the stiffness matrix, we can carry out this multiplication and find a two-dimensional stiffness matrix. And then if we want the compliance matrix, we can just invert that. So now in the idea of plane, in the domain of no strain in Z, the plane strain boundary condition, we have this as our compliance matrix. Right. So if you compare the situation, like we can get a feel for this by substituting in some Poisson's ratios. Imagine if nu is 0.25, then plane strain. We ended up with E times 1.2, 0.4, 0.4, and 1.2, relating the strain to the stress. So this is a stiffness matrix. And for plane stress, we have this one. We have almost just 1 in the x to x dimension, and also a lot lower than we did here for the y strain coupling to x stress, so the off-axis stuff. Now why is this not just 1? Well, 1 would be the coefficient if we were not looking at stiffness matrices, but we were looking at the compliance matrix. It's only the compliance matrix that has a 1 on the diagonal, because that tells you that you get directly Young's modulus if you have no other stress, and we want to just map the one-axis stress to the one-axis strain. When we're looking at a stiffness matrix, the component here is what the direct strain would map to direct stress with, but that's only all of the strain if there's no y strain either. So really, if you have, it's after you would go and invert this and write it in terms of the compliance matrix. In plane stress, it is just this. That's right, plane stress, this one. Okay, so it is just this thing which gives us the 1 when we have the stress related to the strain for plane stress. So this is a stiffness matrix, And that does not have just a 1 in that situation. We're also considering what nu is for that. So Poisson's ratio means that if we have no strain allowed in y, but we do allow strain in z, then the stiffness is only 6.667% higher in the x direction with like one axis fixed. With two axes fixed, that's what we would get by looking at this component. That's 20% higher for our Poisson's ratio of 0.25. Again, the more you stop it from being able to do what it wants, the more you restrain it from moving, the stiffer it's going to feel in the other dimensions. Think about it like this. If you allow it to be totally free, you have no stress in the other dimensions, then the object is going to just move in a certain way, right? That's where it responds. That's how we define Young's modulus. The stress divided by the Young's modulus will give us the strain. What does it want to do? It wants to compress in those other dimensions. Well, if you don't let that happen, you restrict it from doing what it wanted to, then you have to oppose the motion that was going to happen. And that kind of like undoes things. So if you stop it from, let's say, compressing in y by pulling it back out in y, that's going to try and pull it back in x. So it means it didn't move as far as you did, as it would have if you had just let it compress in y, right? So the more you prevent motion in one dimension, the stiffer it's going to feel in the other dimensions. So remember that we worked out that the effective stiffness, if it's totally free in the other dimensions, is just E, and the effective stiffness, if it's fixed in both, is this thing. What about if it's fixed in just one? What's that? Well, it's got to be in between those two, right? It turns out it is. So if you have y and z fixed, and then in the x direction we have this relationship, which gave us this 1700 times for a Poisson's ratio of 0.5, or of nearly 0.5. If it's exactly 0.5, it's infinitely more stiff if the other directions are fixed. Now, if just one of them is fixed, it's not nearly as dramatic, but it is still stiffer than it would have been if they were both free. Let's derive that. The way you can come up with that is, well, there's a couple of different ways. Let's start with the plane strain condition that we derived that has z fixed already, and then we'll just say y is free by setting the stress in y to 0 and looking at how sigma x is related to epsilon x. And you can see that it's going to be epsilon x is equal to this first component divided by E times sigma x. So that means the effective stiffness would be sigma over epsilon, which is E over this thing. All right, so this is, after substituting into it, not as dramatic as this one. There's another way you could have gotten this, and that is not by starting with the plane strain condition and setting sigma equal to 0, but by starting with the plane stress condition where the z stress is equal to 0, and by looking at, here was the plane stress condition, there's the compliance matrix. We inverted this already and got the stiffness matrix, and now if we want to fix y, we'll set the strain to 0 and just look directly. Sigma x is E over 1 minus nu squared times epsilon x. So this should be the same thing that we just derived. And it is E over 1 minus nu squared. Wow, this stuff is heavy. This is a lot. If you're still following along, thank you. Congratulations to you if so. I know what you're feeling. You're feeling, Dr. Minnick, can't we have a break? Can we just go back to doing FlexPDE? Yes. Yes, we can. Let's do some derivations and figure out how this works in FlexPDE so that then we can simulate a lot of these deformations and help visualize and understand them a bit better. So first, let's consider a differential volume, dV, which is dx in dx and dy long in dy in y, and dz long in dz. So this is not necessarily a cube if these are all different sizes, but it's a rectangular prism. And it has forces on it. Let's suppose it only has normal forces. We could have shear forces acting on this, but for this week we're going to pretend that we have no shear forces. This is going to be the case if you set up your external boundary conditions on an object in the right way so that it doesn't try and slide its atomic planes past each other, but just is kind of pulling on them. Right. So under the right circumstances, this is all of the forces microscopically on the object, and what we're going to derive here will work. So the net force in x is going to be this force on the front minus that force on the back. So dfx prime minus dfx. And dfx prime is based on the stress at the front of the object. So that'll be sigma at x plus dx minus sigma at x. And we'll multiply those stresses by the area of this front face, which is dy times dz, to figure out the total force. And using a linearization being that we say that any function at a small distance in the future x is equal to the function at x plus its slope at x times dx, right? This is kind of like a one-term, well, I don't know, two-term Taylor series. We're going to drop the other ones because those ones are, let's use big O notation, order of dx squared. So forget those because dx is very small. We don't need any of the dx squared things, so forget them. We're just going to take a one-term linear approximation to the function, which is going to be okay as long as we do a small enough step. All right, so what if you've got f at x plus dx minus f at x? Well, that's just going to be this thing left over, right? It's just that. So sure enough here, where we have sigma at x plus dx minus sigma at x, that turns out to be just equal to the slope of sigma in the x direction times this dx thing. Aha! So now look at this. The dx and the dy dz could just become dv, and we've got that the net force in the x direction is dv times d sigma x by dx. Similarly, the net force in y and z are going to be that same dv times d sigma y by dy and d sigma z by dz. Now, if there's no net force on this differential volume because it's in static equilibrium, then we need that these things are all zero. Again, this relied on there being no shear forces. We're going to have a more complicated expression next week when we allow shear forces, but for now, it means that each of these slopes of the stresses, of the normal stresses, has to be zero in their respective directions. Right, now we can also relate those to strain via the stiffness matrix, and we can actually relate the strains to the change in displacement of the object, the slopes of the displacement in each of the directions. So let's look at this. The strain in x is the length change over the original length. And what's the length change of this thing? Suppose that we put the displacement at each position as u, v, and w, being the displacement in x, displacement in y, displacement in z. Then the x strain will be the length change in x, the new length, which is the displacement of the front face minus the displacement of the back face. That'll be well, hold on a sec. That's not the new length. The new length would be the position of the front face after it moves minus the position of the back face. But if we just talk about not the position of the front face, but the displacement of the front face, not its displacement from the origin, but it's the amount that it moved after this thing has deformed somewhat, then we've got that, like if the front face moves up by 2 centimeters and the back face moves up by 1 centimeter, the whole thing must have gotten 1 centimeter longer. We take the displacement of the front face minus the displacement of the back face to get the length change, yeah? And you divide that by the original length, dx. So there we have the strain. Okay, so what do we have? Well, if we take the differential equation from Newton's second law, which is that the slopes of all of the stresses are zero, and the regular non-differential equations of the definitions of strain being these slopes, and the Hooke's law relating the stress and strain via the stiffness, then we have a coupled set of differential equations in terms of the displacement components. Right? We can start off with these as our differential equations, and then define the stresses in terms of the strains, and define the strains in terms of slopes of displacement, where displacement is telling us how the object is actually deformed, and then we can find what those displacements are using FlexPDE to solve the differential equations for us. So here's how we're going to do that in FlexPDE. Set up coordinates to in Cartesian 3 for like a 3D beam, and then make these displacements of each point on the object the variables that we're solving for. Then define the strains in each direction as the derivatives of the displacement in those directions. Then define Hooke's law to relate the strains to stress, and then put in our differential equation in terms of stress, based on Newton's second law, that the slopes of the stress have to be 0 as long as we only have normal stresses on this thing. And then we're going to draw out the geometry that this is going to work on and put maybe fixed displacements as values or fixed stresses as loads, and then use some plots and summary reports to figure out the values we want to know, including the deformed shape of the beam. Okay, so what is this going to look like? Well, let's do it for an example. The redo of example 6.5 using Flex. This is where we had the 3 meter by 1 meter by 1 meter steel beam, and we put 10,000 cars hanging from it. So what we're going to do is first set it up in Cartesian 3, and then make these things our variables, and define the strains in terms of slopes of displacement as the variables, and then put in the parameters, the Young's modulus, Poisson's ratio, whatever force we're going to apply in the end, dimensions of the beam. We don't need to do that necessarily. We can draw out the beam later. The way we're going to do this in 3D is by first starting at a point, and then walking over to another point, and then another point, and then another point, and then closing it. This sort of marches out the thing in X and Y, which is drawn a little bit further down. What we do is start at 0, 0, and then go to LX0, and then to LXLY, that draws this part of it, and then to 0LY, and then to close. And then once we've done that, we're going to extrude it in the Z direction with this piece of the code to give it some 3D shape. All right, so now we've got this 3D shape. We'll apply the boundary conditions. And the way that we do these is by setting either values or loads on U, V, and W. And values on U are the most straightforward one. This directly sets the position of U to a certain amount. This says it's fixed to no displacement on the top surface in this case. Load of W equals something would say that we're instead of specifying W directly, we are going to specify the slope of W when it shows up in differential equations. And this is a really tricky thing to explain in FlexPDE. But for the differential equation that we specify, if we specify something like this, this is the differential equation we're going to be dealing with next week. The load of W equals 50E9, negative 50E9, tells you that we are going to have a stress of 50 gigapascals in the negative W direction on this surface. So that is the way, that's what a load boundary condition will do rather than a value boundary condition. So that's where we're going. Let's come back to that in a moment and try to build it up piece by piece to solve this particular problem using this stuff that we just developed. So we want to be in 3D. We'll go to Cartesian 3 here, and our variables are going to be U, V, and W. And because we're not doing time-dependent stuff, we don't need to specify thresholds on those anymore. We can name the problem. Let's say maybe normal elasticity only, no shear. Okay, because we can't deal with shear yet. So let's set up some definitions that we needed as like our Hooke's law stuff. So how do we define our Hooke's law? Well, we're going to need to write out this definition. So first we can write what E is and what nu is for the particular problem. So E is equal to 200E9 and nu is 0.3. Then what we're going to do is write out the relationship. Well, actually, you know what? First, let's write out the strain definitions. And that is epsilon. Well, what did I call them down here? Yeah, just E. Okay, so EX, EY, and EZ. And those are given as derivatives in the x direction of the stresses. So dx of sigma x, did I call it just S? I want to keep the same. Oh, wait a minute. Hold on. These are derivatives of the displacement, of course. So this is derivative of u, and the y derivative of v, the y displacement, and the derivative in z of w. All right, Great. Now, the things that I'm going to use to call the stresses are just Sx, Sy, and Sz. So we could go and write out the equations now. This is the slope of the x stress in the x direction is 0. So let's put that down here. The equation for u is going to be dx of Sx is equal to 0. Why is that an equation on u? Well, because we are also going to define how the x stress is related to the strains via the components of the stiffness matrix. So to do that, we'll write out what the stiffness matrix is. The stiffness matrix in 3D is, let's see, where did we have that? Stiffness matrix is this thing, right? So we can call this like C11 times EX plus C12 times EY plus C13 times EZ, and SY is C21 EX plus C22 EY plus C23 EZ, and then SZ is C31 EX plus C32 EY plus C33 EZ. And then we'll just write out what the components of this matrix are. So C11 is equal to E over 1 plus nu times 1 minus 2 times nu, all times 1 minus nu. And then C12 is the same thing, but multiplied by nu instead. Then C13 is C12, C21 is C12, C22 is C11, C23 is C12, C31 is C12, C32 is C12, and C33 is C11. Right. So what I've just done is made all the off-axis components, this thing we defined for C12, and made all the on-axis components, the thing we defined for C11. Okay, so what do we have? We have our displacement variables. We have our parameters, material parameters. We have our definitions of strains in terms of slopes of displacement. We have our stiffness matrix components for an isotropic material. We have Hooke's law, which relates the stress and the strains. And we have our differential equations, which are okay as long as we have only normal forces. Then for it to be in equilibrium, we need no slopes of x stress in the x direction, no slope of y stress in the y direction, and no slope of z stress in the z direction. And that's the differential equations we're solving. Now this, why is it a differential equation for u? Well, the x displacement is most related to the x strain, and the x strain is most related to the x stress. In reality, they're coupled, right? You've got that even though we're specifying this as the differential equation for u, it will be able to solve and realize the fact that despite us saying primarily use this one to get the next u, it'll couple all of them together and use all of the current values to figure out the next values. Right. The next thing is we want to draw the region. Now, as is, this is specifying a square in the xy plane. And we can have a square, that's fine. We can just leave it as a regular square, but we need to then go and extrude this. And the syntax for doing that is to put in an extrusion segment above the start of the boundaries part. Extrusion is not really case sensitive like everything in Flex, but a little bit easier to notice where the thing starts when you write it in all caps. So we're going to name a surface. Bottom, you can call it whatever you want. So you have to spell surface right, and then it will turn red. So surface bottom, z is equal to 0. Surface top, and z is equal to, let's say 1 for now. Then we can just leave this the same, and it should be able to work. let's see. The only difference is we switched to 3D, so the contour will need to know where. Yeah, so it says where do we want to find this contour? Well, we could say on a certain surface. On Z is 0, say. And here we go. There's our cube. We didn't give it any forces. Nothing happened. All right. So what's next? Let's look at the final displacement by making not just a contour plot, but also a grid plot. Grid of the x position plus the x displacement, y position plus the y displacement, and z position plus the z displacement. So now we're going to be showing what the final object looks like, and there it is. We can rotate it around. We didn't put any stresses on it yet, so nothing happened. Okay, what else can we do? Let's mess with the boundary conditions. So the easiest way to do this is to do them in Z first. Let's imagine the Z surface is fixed to value W is 0, and the top surface, we're going to force it, value W equals 0.2. We're going to give it a displacement that's going to extend it by 20 centimeters up. Now what we expect when we do this and take the cube is it's going to stretch upwards in Z. Let's see. So it's saying we're not allowed to do that. Oh, right, because that's not how you specify boundaries on this thing. We need to put that in the boundaries section. So first let's go in here and we'll say surface bottom, same name we gave it up there, value W is 0, surface top, value W is equal to 0.2. Stretch it to a displacement of 20 centimeters on the top and hold the bottom still. Let's see what happens. Okay, look at that. You can see it's stretched up, right? It has not done anything. Well, it's compressed in a little bit on the sides. Let's exaggerate it a bit more. So now it's stretched up more and compressed in on the sides. What else can we look at? We can look at what the stress will be when we've stretched it up like this. So let's find out how much stress we need to be able to do this. So let's do a contour of the Z stress on Z is equal to 0. And it looks as if we have a uniform Z stress with a value of 8 times 10 to the 10 pascals. So this is telling us that when we stretch up this thing by 40% strain, it's 40% because we made it 1 meter by 1 meter by 1 meter. So when we put the top to 40 centimeters up, then it's a 40% strain. And that says that for this particular material, to stretch it by 40% when the other sides are free is going to take 8 times 10 to the 10, which is 80 gigapascals. So can we work that out in a calculation way? Well, here's some maple that has in it the compliance matrix and the stiffness matrix from earlier. And what we can do is write out how these are related to the stress and strain. So we can say that epsilon, or maybe ep, is equal to a vector, fx, fy, fz, and we'll say that sigma s is equal to a vector, sx, sy, and sz. Okay, then what's true is that the relationship between these two is done by these matrices. So you could say either that epsilon is equal to the stress, but left multiplied by the compliance, right? So the more compliance times the stress, the more compliance you have, multiplied by the stress, the more strain you're going to get. Or you could say that the stress is equal to the strain, but left multiplied by the stiffness. This is the one that we did in FlexPDE, right? We wrote out that the stresses are given by the strains after left multiplying that whole thing by the stiffness matrix. Okay, so if we have a situation like we have here, where we've got it free in y and z, then what we're specifying is that epsilon in y is unknown, but the stress in y and the stress in x are both equal to 0. The strain, though, in z is equal to 40%. We specify that. We set that it has 40% z strain. So what this tells us is not really easy to see from this formulation, from using the stress times the strain, because the strains are mostly unknown. There's a lot of unknowns in there. But using this formulation, it's more obvious what's going on. You can see that the z stress needs to be 40% times the Young's modulus. When we know most of the stresses, then it's usually easier to use the compliance matrix multiplied by the stress to see what the strains are directly. Okay, so that means in this particular case, we're going to have 200 gigapascals as the stress, so that's sort of a bit rough to see, but we could solve the third component of this equals the third component of that. I mean, you could just left multiply it, just like multiply it out and say, all right, well then SZ is equal to 40% of 200, and that's equal to just 80 gigapascals. All right, and that's what we got there. What about if we do something different? Can we explore this maybe by fixing the other dimensions? Yes. So if we instead make epsilon x equal to 0 and epsilon y equal to 0, so we stop it from straining in the other dimensions. Now, the first formulation is not so obvious what the z stress is going to be, but the z stress is directly determinable from the second one. Now it's easier to have Maple multiply this for us, so we'll uncomment this and see what stress we expect if we fix it from moving in the other dimensions. And it looks like we're going to have 107.7 gigapascals. So how do we do that in Flex? In FlexPDE, to get it to stop moving in the other dimensions, we'll apply boundary conditions on the x and y displacement. So value of u is 0, value of v is 0. Okay, and we'll do that on the bottom surface and on the top surface. But this isn't going to work. Let's look. So the problem is it still is able to move in because of all the sides there, and we don't have this 107 gigapascals. It looks like it's just sort of 98.7 gigapascals. So how can we fix that? Well, we also need to apply the boundary condition on the sides, and that's from this x-y mapping here. So it turns out you can do it for just one, and then it'll continue until you change it. So if we just set this right after the start point, then when it's going to 1, 0, to 1, 1, to 0, 1, and to close, it will exist for all the rest of that. So now it holds it still on the sides. It doesn't allow it to compress in, and this gets us all the way up to the 107 gigapascals we were expecting. Another reason why we really want to do that this week is because when we don't specify this on the sides, then the calculation is actually just flat out wrong. This is going to give rise to shear stresses on the sides of it, and we ignored those when we wrote these differential equations, right? These only work in the event that you only have normal stresses acting on the sides of it. So we definitely need to set up our problem to have no shear stress this week for the calculation to be right in FlexPDE. All right, so let's go and change up the FlexPDE and the Maple code to solve this problem directly. So what we need is to be dealing with a 3 meter by 1 meter by 1 meter steel beam that we are applying a stress of 200 meganewtons in X. So this tells us that Sy is 0, Sx is 200 E6, and Sz is 0. And we don't know what the strains are. And we want to know what those are, so we can get the strains more easily by using the compliance matrix in the Maple formulation, which just tells us directly what these strains are. This is something we calculated earlier. All right, well, what about in FlexPDE? So this is a problem where it's really overkill to even use FlexPDE at all. How do we reproduce these strains in that? Let's lay out the, we don't even have to set the right geometry yet. All we really need is that the stress is 200 meganewtons in the x direction, and there's no stresses in the other directions. So we can do that by getting rid of these boundary conditions on the top and bottom surface, and instead finding out which one is the x surface here and putting a boundary condition on that. We need it on the positive and negative x surfaces. So let's see. Here what we do is we change x. We have y equal to 0, and then we walk to 1, 0. Oh, first, let's kind of separate this out. You can do it like this, and that doesn't change anything about the problem. Okay? Still draws exactly the same shape. We've just split it into 4 different line commands. This first command, after we start here, start at 0, 0, then we're going to walk to 1, 0. So what's in here is the thing, this is the set of boundary conditions when y is equal to 0, right? So first we have, well, y is equal to 0. We're going to go starting at this point and then apply a new boundary condition and then change the x value to this. So we're holding y equal to 0 and we're changing just the x value. So this is the y equals 0 surface, right? Maybe we'll put this like there. Y equals 0 surface is the boundary condition we put right in front of this thing. And then the one in front of this thing would be x is equal to 1 and we're changing y. So this is the x equals 1 surface. And for this one, we're going to put a load in the x direction is equal to 200E6. So 200 megapascals will be the stress that we have in the x direction. Yeah? Next, this surface, we have y equal to 1, and we're changing x. So this is y equals 1. And now the last one, because from where we were at 0, 1, and we're going to go to 0, 0. We're holding x equal to 0 and changing y. So this surface here is the x equals 0 surface. So this one we need to set value of u is equal to 0. The problem is these boundary conditions exist until you change them. So once we've set load of u is equal to 0 on this surface, if we don't get rid of it on this surface by changing the u boundary condition, specifying either a value or a load on u, then we're going to still be applying this 200 meganewton stress in the x direction on this y surface, and that's a shear stress. So this is going to not work. We can't deal with shear stresses. The thing's going to be all funky. Well, it wasn't that funky actually. This is because the stress that we're applying is not very big, right? So we need to magnify the displacement to be able to see this. And one way to do this is by multiplying each by magnification. And we'll set this parameter 1,000. So let's look at what things are doing. Yeah, that's that's no good. It was supposed to move just 3 millimeters. I guess if we multiply that by 1,000, that's kind of a lot. That's like, it's sort of folding in on itself. Let's multiply it by 100 only. Right, so you see some really weird stuff. This shouldn't be happening. That's from shear that we're not dealing with. Our equations don't handle it. So let's get rid of that load on the y equals 1 surface by putting it back to load of u is equal to 0. That's sort of the default one. When we don't say anything, it's the same as saying that. So up here, it's like there's no stress on all the different surfaces in their directions. And same with this first y equals 0 surface that exists while we draw this line. Okay, so now we are indeed having it stretched just in the x direction. And we expected from our maple results that the strain is 0.1% and 0.03% in the other directions. Let's report that. So what we can do is pick somewhere in the middle of the object and then go and insert a summary section to report the strain. So here we go. We'll say summary and then report epsilon x. And where do we want to report this? So because we need to evaluate this at a point, we'll need to say report the value of this and then give coordinates at, let's say, 0.5, 0.5, 0.5. Sure, right in the middle of this thing. So now if we report that, we're reporting the strain right in the middle. Epsilon x is 0.1 e minus 3, and that should be what we got in Maple. Yeah. And what about the strains in the other dimensions? Do we need val here? Can we just get rid of that? Report ex? Doesn't allow it. So what about if we do at that? Nope, doesn't allow it. So we need to specify report the value of ex and then the coordinates, which in 3 space means we need 3 coordinates. We can also report values of the other strains, ey and ez, all at the center of this cube. We could have picked some other point that should be uniform. It shouldn't be depending on where we're at. And indeed, we got this 0.03% or 0.3 e minus 3. Yeah, a third, roughly, not quite a third, but 30% of the strain that we got in X is what we got in both Y and Z. So this reconfirms what we had in Maple, and also notice the negative, it is compressive in those directions. All right, how do we make this actually the right size in X, Y, and Z? We just need to change how much we're extending it in X. So we can go and type this in by changing this not 1 meter, but to 3 meters. And now it'll start off at this extension here that doesn't actually change the strains that we get because we're applying a uniform stress. Or if we're going to be, rather than typing it in 2 spots, you can just put these in terms of variables. We can say this is our variable Lx, and this is our variable Ly, and then this is our variable Lz, and then specify what those are up here so we can now have those set right at the start and change them around more quickly. Yeah, and there you have it. So that's how you can apply boundary conditions of stresses or displacements in FlexPDE and use that to see the deformations of objects and confirm what we're calculating using Maple. We'll look at some more advanced examples of this in the practice problems.